Hey folks, me again. Hopefully you looked over one or two of the sample problems in the packet. I'm now going to dig into example number 2. Again, I'm going to end up with a net ionic equation, but that's not really the goal. The goal is to explain how an acid or a base added to an insoluble or slightly soluble compound can cause an increase in the solubility of that compound. So here we're looking at solid calcium carbonate, and we're going to add some hydrochloric acid onto it. So again, if all I were doing were writing net ionic equations, I would just dig into writing the net ionic equation. The purpose of this is to look at how an acid added onto one of these slightly soluble compounds can affect the shifting equilibrium. So the calcium carbonate is a solid. We go pouring hydrochloric acid onto it. The first thing that's got to occur and will occur is some of that calcium carbonate will ionize, but not much. It's got a very low K value. So being that this K value of reaction number 1, just like example 1 that I posted a minute ago, the K value of reaction number 1 is less than 1. So it doesn't occur much, and thank goodness. Think about ancient societies like the Greeks that built the city of Athens. So in the city of Athens, there's the Parthenon, there are all these ancient marble statues. Well, marble is made of calcium carbonate. And so this kind of comes up because we've already talked about the formation of acids by combining oxides with water. Non-metal oxides, when combined with water, produce acids. Well, when you and I burn materials, fossil fuels, wood, etc., it releases non-metal oxides into the atmosphere. Those non-metal oxides end up combining with water to produce acid in the upper atmosphere, and we refer to that as acid rain. So you might be wondering, where exactly does this apply? Well, this is a good example. So just like in example number 1, I'm going to ignore the chloride. The chloride will end up being a spectator ion. In other words, we'd form calcium chloride, and the calcium chloride would be soluble according to rule number 3 in the solubility rules. And so might as well just ignore them now, otherwise we have more to deal with later on. And so the hydrogen ions, being positive, are clearly attracted to the negative carbonate ions. And I don't know that I did a great job of explaining that in example number 1, so maybe I'll backtrack to do just that. So if you think about magnesium back up here, magnesium hydroxide. So the magnesium ions are actually repelling the hydrogen ions. And so the hydrogen ions are attracted, since opposites attract, the hydrogen ions are attracted to the hydroxide ions, hence the formation of water. So a similar deal here. The hydrogen ions are attracted to the carbonate ions, and so what we'll end up forming is carbonic acid. And carbonic acid, I hope you vaguely remember, both from honors chem and earlier in the year, that carbonic acid is one of those that is very unstable. And so it will form, but then immediately begin to decompose into water and carbon dioxide. And again, I don't happen to know the actual K value for this reaction, but I know it's much, much greater than 1, hence driving this into a completion system when we add the reactions together. And so the carbonate ions will cancel out. The carbonic acid is already canceled out. So what we've got going on is calcium carbonate reacting with a pair of hydrogen ions to form water, carbon dioxide, and that calcium ion. And again, the overall K value for this reaction would be much, much greater than 1. In other words, indicating that this would be a completion system. So kind of like what we were looking at up here, how does the second reaction affect the hydroxide? Well, here, notice reaction number 2 is going to ultimately cause this system number 1 to shift to the right, producing a high concentration of carbonate, which is immediately reacted with the hydrogen ions. So ultimately what we end up with is a reduction of carbonate ions in the solution. And as the system shifts further, and as system 1 shifts further and further and further to the right, so we get more and more of the calcium carbonate dissolved. So again, back to Greece and the city of Athens and all these marble structures like the Parthenon and other various statues that are outdoors. As acid rain descends on those structures, the marble, being calcium carbonate, is dissolved more and more and more. Clearly a problem if you're trying to preserve some of these ancient structures of historical value. And so they've taken measures. I'm not exactly sure what they've done, actually. Some of them they've covered, some of them they've put protective coatings on, and other restorative means. I'm not exactly sure on all the details there. Now, before I dig into example number 3, I'll let you, again, go back to some of the homework problems in the packet, review some of those, attempt some of those on your own, and then by all means, as questions pop up, for certain, let me know, and I will do what I can to help you out. You can email me, or you could put send me messages through Schoology, one or the other, and then I can post videos if that's pertinent, or just respond to you individually if I think that's all that's necessary. Anyway, let me know if you have questions, and I'll post those. I'll put up another video here in a few minutes about example number 3. Take care.